Why do we call the same reddening effect to different things, depending on whether it happens near a black hole or across the whole universe? In the energy filament theory, redshift is primarily a rhythm mismatch caused by the environment changing the internal timing of matter. So the color shift logic should not magically switch languages at cosmic scale. Start local, near the supermassive black hole at the center of the Milky Way. Starlight can be shifted as it climbs out of a deep gravitational environment. Even sunlight shows a tiny overall shift. Mainstream physics calls this gravitational redshift. And the causal chain is straightforward: stronger gravity changes how clocks tick. That is not just a metaphor. Atomic clock experiments literally show the same kind of clock ticks differently at different heights and gravitational potentials. The internal oscillation rhythm of matter is not an untouchable constant. It is slightly environment dependent. So the logic is, environment changes the rhythm. Rhythm changes the emitted frequency. Frequency shift makes the spectrum slide red. Clean. Now zoom out to the entire cosmos, and the story abruptly flips. The same kind of spectral sliding is no longer described as rhythm changed, it becomes space expanded. Particles and their emission rhythms suddenly get treated as fixed backgrounds, while geometry becomes the sole actor. That is a huge logical switch, and it should at least raise an eyebrow. Why didn't standard cosmology simply extend the local logic, gravity plus rhythm evolution, to the cosmic case? One practical reason is that it must fit not only how red, but also how dim. The brightness-redshift relation from supernova. In the usual framework, pure gravitational redshift alone struggles to match the observed Hubble curve shape. So the model leans on expansion geometry, and later adds acceleration and dark energy to make the curve work. But here's the twist. Once you allow the yardstick itself to evolve, the old dilemma changes. In this picture, the universe is an energy sea relaxing from tighter to looser tension. Earlier epochs correspond to a tighter sea, and in that tighter sea, the internal rhythm of matter can be different. So when we look far away, we are looking back in time. We are comparing light emitted under an older rhythm to our current rhythm. It is like using today's faster metronome to judge a song recorded when the studio's metronome was slower. The tracking is not wrong, your reference changed. The result is a systematic shift. What is normal color there can look redder here. Now ask the obvious follow-up. What about farther looks dimmer? That part is almost too normal. A flashlight looks dimmer when it is farther away. In the universe, distance also means delay. The farther an object is, the earlier the light you received was emitted. So dim first tags distance, and distance naturally tags earlier. In this picture, earlier also tags a different sea tension state and a different matter rhythm. So red and dim become two faces of one story. The sea evolves, the rhythm evolves, and you are reading old lights with a newer clock. That does not automatically prove the idea is right. But it proves something simpler: redshift is not forced to be a speedometer for space running away. The key point today is just this. Modern cosmology is comfortable saying, on small scales, that gravity changes clock rates and therefore changes color. Then on cosmic scales, it often acts as if only expansion is allowed to touch the spectrum. Once you admit that redshift as rhythm evolution is a coherent alternative language, expansion stops being the only story on the table. And if expansion is not the only story, then questions like a real cosmic boundary and structures like the silent cavity are no longer taboo. Tap follow, share it on New Physics, Clear Universe.